You go.
Good. Hi, everybody. My name is Matthias Carlson. I'll be the moderator for today's webinar. Together here with me, I have Professor Curtis Hayes Whitson, which is going to be the presenter for today. And we are going to discuss equational state tuning, what's important and why. First, just a few meeting logistics. We have more than 400 registered participants, which is great. But obviously that leads to every one of you having to be muted, unfortunately. So if you have any questions or suggestions or feedback, please feel free to use the chat or Q&A section that's on this WebEx event system. And I've indicated it here in this screenshot on the slide in front of you. We have about 1 hour of presentation material about the main topic, equation state tuning, what's important and why. And after that, we have about 1 hour at least set aside for potential Q&A that we get throughout the session. Important to emphasize is that this session will be recorded and also made available on Whitson Academy, which is our online learning platform, academy.whitson.com. On Whitson Academy, there we essentially offer live virtual courses, live topical webinars such as this, on-demand pre-made courses that you can access on demand when it suits you, and also different how-to videos to, for instance, learn how to import PVT tables into different simulators or processing packages. Some example courses are typically courses related to what we offer through Whitson, which is PVT and phase behavior related topics, gas EOR, gas condensate reservoirs, and very important to emphasize is that we try to cater all kinds of different levels, everything from beginners that are just getting exposed to these topics, all the way to expert and advanced users.
And actually, all three of these topics are covered for both conventional and unconventional versions of the course.
Yeah. Perfect. And I'll just show you all that just real quick here. So Whitson Academy, academy.whitson.com. You can go there yourself. And this particular webinar will be put under Whitson webinars. So if you click there, we'll get this particular recording up here a little bit later, hopefully today. Good. So just flipping back to this presentation. The next course that we'll offer is actually an advanced black oil PVT course. It's going to be a free course, which is going also to be live half a day in August. The date is set to be 18th of August 2020. And the times is also provided there. And in terms of time, we've been trying to accommodate all the different time zones, so at least it should be possible, whether you are in Calgary, Canada, or in the Middle East, to participate. 2 slides on essentially a little bit introduction to the topic today before I'll introduce Curtis and he'll take the rest of the presentation. So what we are going to discuss today is equational state models, and for those of you who are well aware of equational state models, you probably know that 99% of the time, at least in the petroleum engineering domain, we typically use the so-called Peng-Robinson equational state, or the so-called SRK equational state. And if you ask someone in your company to send you an EOS model, what you typically get provided is 2 tables with which is the component property table and the binary interaction parameters. And Curtis will show these equations in his presentation, and you also get a little bit more familiar about why different terms were introduced and what these 2 tables actually represent. What we use an equational state for in the petroleum domain is to be able to represent the PVT and phase behavior at different pressures and temperatures for different compositions. So on that note, I'd like to introduce Curtis Hayes Whitson. He's the CEO and founder of Whitson. He's also my boss, and he did his bachelor's degree in petroleum engineering at Stanford in the late 70s before he moved to Norway and did his PhD at NTNU. He's published a lot of different papers throughout history. Actually, all of them are available upon request through our webpage, whitson.com. And he has also published 2 different books, one Well Performance that he wrote together with Michael Golan, and probably more known, the SB Face Behavior monograph that was written in 2000 with together with Michael Brule. Worth mentioning in terms of recognitions, Dr. Curtis Hayes Whitson received the Anthony F. Lucas Gold Medal back in 2011. And on that note, Curtis, I'll just give the word to you.
Okay, guess I need to share.
I'll have to make you a presenter here. 1 second. Now you can share the screen.
All right. Okay, I need to flip to, let's see, and then I need to, Control Q to get rid of these. There we go. And getting closer. There we are. A little pointer here, and thanks, Matthias, for the introduction. And this is a pleasure for me. Webinar. I've sat in on a few and listened to other folks talk about different topics, and it's the first time for me. So hope it goes well. I guess the biggest problem is for me is not having you where I can see you, and make sure that you're staying awake. But I have to live with that. Hopefully the questions that will come through, even though you're not talking or sending the questions written, that'll work as well. I wanted to make sure with this extra hour of Q&A and discussion that we would have enough time to really talk about things, and I wouldn't just be talking for the full hour and not really have time to have some question and answer type things. So the topic is EOS tuning, what is important and why. It's a topic that, I've been involved in for pretty much my whole career. I followed those who had been the pioneers in this area. You'll hear about some of those. I'll get some history of this topic, starting in the mid-1960s when I was only 10 years old. And I actually have had the fortune of knowing some of the people who were real pioneers in this area. Ken Starling, for example, and certainly Keith Coates. And so a few things I've done have been used by others in doing EOS modeling. And so it's been fun to be part of this long journey. And I'm going to try to share you my perspective on it. And in particular, what I consider important and why I think it's important. This is a major area of research for me, has been always. It's a major area of the consultancy work that we do at Whitson. And a few of my colleagues who are with me in the room today are the ones who really are executing this topic on a daily basis. And so hopefully they'll correct me when I say something wrong. So we'll get started here and talk about the goal of EOS tuning up front. And basically that is to create an accurate equation of state model that describes relevant and important lab PVT data that have been measured on your fluids that have been sampled. But to do this for every sample that is going to be modeled in your engineering calculations. That could be a single well, but more than likely it's multiple wells within a reservoir. It could be multiple reservoirs within a field. It might even be an entire basin. And we've actually developed equation state models for the Montney, for the Eagle Ford, for the Bakken basins, and the Permian as well. So this is in some cases possible to do such a comprehensive EOS tuning exercise, but it's it's basically it's a challenge, and we're going to talk about some of those challenges. Now, the one constraint that we always have is that the EOS that you develop should be consistent, thermodynamically, physically consistent. And we'll look at some of the checks, QCs that we do to make sure that's the case. Now, how do we do EOS tuning? It's a manual trial and error, but automated process using nonlinear regression methods. Basically, we modify the default EOS model parameters. I'm going to be calling those variables. We'll talk about what are those parameters. And in addition to the EOS model parameters we're changing, we're also going to be changing slightly each and every sample composition because of the lab uncertainty in measuring the mole percent methane, ethane, propane. So the numbers they give you in the lab are not set in stone. They actually can and will normally need to be adjusted slightly in a consistent way. That's part of the EOS tuning process. And what we want to do is minimize the mismatch or maximize the best fit, so to speak, of the EOS model versus all of the available lab PVT data. So this is a partly automated method, but basically you're running the automated regression tens, if not hundreds of times before you find the final model. So why do we do EOS tuning? Well, basically, no one has given a methodology, a procedure to create a default equation of state that can predict all of the complex phase behavior, miscibility, retrograde condensation, extreme vaporization and gas injection projects, volumetric behavior, gas condensate, liquid dropout of petroleum reservoir fluids, accurately based only on the measured composition. So we don't have a way to come up with a set of EOS model parameters by default or some way that will give you all of these properties being calculated accurately. So that's basically why the EOS models that are default aren't good enough to predict complex phase. Now, back in the mid-'80s, there were a few people, most people realized that this was going to have to be EOS tuning was a requirement because you had work all the way back in the 60s. We'll look at it and into the 70s. People looking at even the simple systems, binary systems, single component, and simpler systems where you needed to tune the equation of state parameters to match measured laboratory data. There was one paper written by Karen Pedersen, Per Thomason, and Olga Frenslund, where basically they had advised against doing EOS tuning because they didn't feel that it would provide a consistent, valid model. We'll come back to that. The last part of the presentation, the webinar, we'll talk about the history of EOS modeling, and we'll return to these statements and to why we believe, in fact, that this is not correct. And I believe that Karen and the company CalCep and PVT-Sim, they now offer model tuning for the equation of state. So Matthias introduced very briefly the equation of state model input data, which is basically two tables, component properties and BIPs. And I'm just going to go through and show where those component properties show up. So basically, we've got pressure is equal to RT over V minus B. The V is a molar volume, and total volume divided by moles, minus A divided by a denominator term that has volume squared, and the term B again. Now, in addition, we use in doing equation of state modeling, we use the Z factor, which is a formal definition related to PV, T. It's a dimensionless quantity applied to both gas and liquid phases. And then in order to use the equation of state for calculating transport vertically under gravity, you need to calculate mass density. And to calculate mass density, you can't work with molar volumes or molar densities, which would be the inverse. You have to have mass density. And here you need the molecular weight. So the constants A, B, and there's a constant C here, which I'll need to give, let's see here. Basically, in 1981, the volume translation method was introduced, and this basically took care of the deficiency of the two-parameter A-B equation of state, which would include, basically this would be examples of the two constant equation of state is the SRK and the Peng-Robinson. And the liquid volumes, liquid densities, were off by as much as 5 to 35% using only A and B. So they introduced and said that, well, if you want the accurate volume, you need to take the two-parameter equation of state volume solved from this and subtract off a constant. And that constant will be different for each component, just like A and B is different for each component. Now, A is defined as a numerical constant. This is typically around 0.4 times R squared TC squared over PC. So basically you see critical temperature and critical pressure being the requirement to calculate A. In addition, you've got this correction term, alpha, which we'll come back to. And alpha makes sure that the vapor pressures of every component are calculated accurately. And Suave was the one who introduced this equation that both SRK and Peng-Robinson used. But what you see is that it needs this term M. And Suave, as well as Peng and Robinson a few years later, they correlated how M varied as a function of component using the acentric factor. So now we've got three component properties that we need to know for each and every component in our mixture: TC, PC, and acentric factor. In addition to that, you need molecular weight. And with the Penelot volume translation, we need this constant C, which is normally introduced through a dimensionless quantity, S. Some programs will allow you to input C with the molar volume unit. Most use the dimensionless term S. So basically we've got TC, PC, acentric factor, and S together with the molecular weight. That gives us 5 properties that we need to know for every component. So that table 1 Matthias was talking about is these 5 properties for each and every component. In addition to that, the second table requires the binary interaction parameters, and those first come when you have mixtures of at least 2 components. So the A, you can use the exact same equation, A, B, and C, the same equation relating pressure, volume, and temperature for mixtures if you calculate the average A, the average B, and the average C. I'll go ahead and write that average C here. Is a linear mixing rule just like for B. And the mole fraction, UI, written here generically, can be the total mole fraction of the mixture. It may be, if there's an equilibrium liquid and vapor, it could be the equilibrium vapor phase composition, equilibrium liquid phase composition. So A will be different for the vapor and liquid because the compositions are different. So basically in this equation here, there's a correction term here. This is a correction term to improve the ability to calculate vapor-liquid equilibria for mixtures. And typically, you assume it's going to be close to 0, but for most compounds, it'll range somewhere between 0.01-ish and 0.2. Can be positive or negative. The BIP, as we call it, binary interaction parameter, is a symmetric parameter. So C1, C10 binary is identical with C10, C1. So it's a symmetric matrix. And the binary interaction parameter may also be a function of temperature, as was the volume shift, maybe as a function of temperature. So these are the equations that are used for mixtures. And they're used specifically to solve phase equilibrium problems, in addition to calculating density of phases. So here we need to use chemical potential from Gibbs or the fugacity. They're related in a very simple way here. And to calculate the chemical potential or fugacity, you need the volume of the phase, the average A and B of the phase. You need the individual component A values and the composition of either the phase or the mixture. With that, you can calculate the chemical potential. And what's required for equilibrium is that the two phases have the same chemical potential. Methane has the same potential in vapor as methane has in the liquid. And when you solve this set of equations together with the material balance, that gives you what we call equilibrium ratios, which are defined as the mole fraction equilibrium vapor, yi over the equilibrium liquid mole fraction xi. Now it ends up that EOS model tuning, if it's done properly, doesn't really have a problem in predicting accurate densities, okay? Without any tuning at all, more or less. If you do the characterization of the heavy component, C7 plus characterization up front, if that's done in a proper way, then the gas and oil densities will always be matched within 1 to at maximum 3%, without any tuning related directly to the density data. Most of the data that you have a hard time matching will be related to or dependent on the K values. So EOS tuning is controlled by PVT data mainly dependent on K values. For example, saturation pressure, the type of saturation pressure, be it bubble point or dew point, the equilibrium compositions, yi and xi, and oil relative volume. How oil shrinks below the bubble point or how oil condenses below the dew point. Those properties are the difficult properties to match when we're doing EOS tuning. And they're related to the K values. And the K values are related both to the critical pressure temperature, acentric factor, as well as the binary interaction parameters. So these are the parameters that we can change to try to improve the prediction of these PVT properties. Now, why are we justified in tuning the equation of state? And this goes back, I mean, it was pretty obvious to most people in the 1980s, those who understood petroleum mixtures. Well, the first thing is that the cubic equation of state doesn't really describe very accurately for a pure compound very high pressure volume relationship, basically the isothermal compressibilities. So if you've got a reservoir pressure at 900 bar, the cubic equation of state cannot be tuned to give you the correct compressibility dependence on pressure, giving you recoveries from initial pressure down to, for example, the saturation pressure. It just can't be done. It's the wrong form. The cubic volumetric dependence is wrong for these high pressure systems, be it liquid or vapor. In addition, if you're right near the critical point of a single component, how pressure volume changes it's not badly predicted, but it's not according to thermodynamic behavior of how actual pure components behave. So you've got even for single components. In addition, for single components, Suave got the vapor pressure predictions correct by changing alpha, changing the A term by introducing a correction term, alpha, to get the vapor pressures correct. But vapor pressures are only measured at temperatures less than the critical, okay? But if you look at methane, for all reservoir and surface process conditions of pressure and temperature, methane will be at a reduced temperature greater than 1. So what value of alpha should we use for TR greater than 1? Should it just be no correction at all? Well, no, that's not what we do. The Suave, the SRK, and the Peng-Robinson both extrapolate this subcritical alpha term to supercritical conditions without having any phase behavior for methane to tell you how it should be extrapolated. There's a real good discussion of this in the book by Mikkelsen and Mollerup. And the point is that the A value for methane, the most important constituent in the mixture, in most petroleum mixtures, is not going to be right. So in reality, you have the right to change A for methane because of this. The other thing is that if you got binary systems, even for very simple methane propane, methane decane, and you look at the phase behavior of binary, basically that's given by, well, let's say methane, the vapor pressure of pure methane here, that's its phase behavior. The decane, for example, vapor pressure curve here, it ends at the critical point. And if you make up mixtures, let's say 70% methane, 30% decane, you'll get a phase diagram, pressure temperature phase diagram, with bubble points, dew points, and a critical point. If you go to a 30% methane, 70% decane mixture, you get a different phase diagram, a different critical point, different bubble points, different dew points. If you just go straight and predict the critical locus and these individual phase diagrams of simple binary systems with, be it the SRK or the Peng-Robinson equation of state, you will not predict things that are engineering accuracy correct. It'll be off. It won't predict it within engineering accuracy. And so what we have to do is introduce this binary interaction parameter between, for example, C1 and C10 to get a better overall fit of the critical locus and the individual phase diagrams. So it's even for simple binary systems, we have the need for tuning. And by the way, maybe for this mixture here on the left, you'll need one binary interaction parameter and you'll need a different binary interaction parameter for the higher temperature system. In addition to that, we have many, many components, hundreds, if not thousands of components that we don't even know what they are. We don't know paraffinic, naphthenic, aromatic, the heavy components. We don't know the hydrocarbon makeup, the fidelity, if you will, of that component. So how are we going to know its critical pressure, critical temperature, eccentric factor, even the molecular weight? We don't know them. They're known approximately based on correlations of, we can measure an average boiling point, an average specific gravity for a particular heavy cut. And there are correlations to get estimates of TCPC eccentric factor, but we don't know that value with any exactness like we know it for methane, ethane, and propane. So that's another reason. In addition to that, we don't know how much exactly we have of those heavier components. Chromatographic analysis is great. It's getting better all the time, but it's just basically, it's not known exactly. Is it 0.003 C35 or is it 0.005? You don't know, okay? Some labs will give you the one number, some labs will give you the other number. So not knowing the amounts, the complexity and wide range of pressure, volume, temperature, composition for petroleum mixtures, particularly gas condensates, oils undergoing gas injection, miscible gas injection. So you can kind of see that it's a difficult task when it's not even getting the single component and binaries accurately. Now, on the other hand, you get a lot of cancellation of error, in fact. So the cubic equation of state has been shown, and it's been shown since the 70s, to give very accurate description of petroleum mixtures. And in the early 80s, it was even shown to give very good description of very complex petroleum mixtures. And we'll look at some of those publications. So you are able to do it, but you don't know all of those two numbers in the two tables a priori. So the question is, we've got so many parameters that we have, okay? We've got 5 properties for every component, okay? And this huge matrix of binary interaction parameters. So how do we prioritize the variables that we want to change in the equation of state? Well, this is kind of the simple recipe. Every software will give you different ways of doing this, but basically the properties you don't know very well or at all, those properties can be changed more than properties that you know well or exactly, okay? So the so-called C7 plus component properties are definitely on the list of what you can change and will normally have to change in some degree. Less so for C7 than for C30. They're most uncertain. In fact, the unfortunate thing is that they're the components that usually control the phase behavior of gas condensates. You know that the dew point and the liquid dropout curve is controlled by the distribution and properties of the C7 plus components. For oils, of course, methane is much more important, but if you do gas injection and have a complex condensing, vaporizing type miscible displacement, then all of that condensation, vaporization is being controlled by the very heaviest components. So basically, all of these C7 plus components have a big effect on the calculations, and they have a significant amount of uncertainty. And the greatest uncertainty is in this very heaviest component. And we've got all these BIPs, and in particular, what people have shown is that the BIP between methane and C7 plus components, and in particular, methane and the very heaviest component, these are really the parameters that are most useful in changing the K equilibrium K values for components to make better matches of saturation pressures, liquid relative volumes, and so forth. Occasionally, now usually non-hydrocarbon, hydrocarbon BIPs, you just take them out of the table and use them. They've been determined with all the binary data out there. But if your injection gas or your reservoir fluid contains a large content of the non-hydrocarbons, then you're likely obliged to change some of those default binary interaction parameters to get a good engineering fit of that type of data. But the requirement is that you either have a lot of those components in the reservoir fluid and or that you're injecting gas containing the non-hydrocarbons. Third on the list is that every composition you get from the laboratory has uncertainty in it. So we're going to need to change the reported laboratory composition, ZI, mole fraction, for each sample a little bit differently. And we can do that in three different ways. The one is that because what they measure in the lab are mass fractions, we have to convert those to mole fractions. Not knowing simply one molecular weight, for example, the C36 molecular weight accurately, will affect the mole fraction calculated in that conversion from mass to mole for all of the components, not knowing just one molecular weight. And in fact, you don't know the molecular weight probably of C10 through C35 in addition to C36 plus. So you've got you can change this molecular weights of the heavier components. When they come up with compositions, they always have to do some kind of recombination. If you have a reservoir MDT sample or a bottom hole sample, the lab has to flash that down to standard conditions. They get an equilibrium gas and an equilibrium vapor, an equilibrium liquid. And the amounts of the two phases at standard conditions are not known exactly. Okay, these are laboratory measurements. So there's some uncertainty in what that recombination ratio should be. And finally, this GC gas chromatography analysis leads to a considerable uncertainty in the amount of the very heaviest components. And that's because of what we call baseline shift and internal standard, which are both methods that try to improve the amounts of the heaviest components, but they don't get it right exactly. So we use the gamma modeling method to try to remove some of those uncertainties and identify erroneous data, not as part of the tuning necessarily, but as a pre-processing to the EOS automated EOS tuning. And then finally, you may find that changing some of the other BIPs amongst all of the components is useful, but you have to be careful there. So this is the list of the variables. Now this is just kind of a sketch of, you got all the components here on the left, okay, non-hydrocarbon C1 to C6. Basically, we know all of the properties, TCPC acentric factor, the volume shift. We know all of those properties, molecular weight. You don't want to mess with those. You could argue that you can change methane A because we don't really know how the extrapolation of alpha should be done, supercritical conditions, but basically we almost never adjust properties of these lighter components. That's 10 components you can take away, 10 or 11 components. Now the C7 through C9 or C10, today in modern laboratory analysis, we basically know what all of the different isomers are in those single carbon numbers. So we know the properties pretty much of all of those C6, 7, 8, 9, maybe even 10 reasonably well. So if you're going to change any of the properties, you don't change them very much. But then comes these unknown single carbon numbers, C11, 12, out to, let's say, it might be out to C24 in the year 2000. But today we go out to C36 plus. So all of those properties of single carbon numbers and then the remainder, the C36 plus, for example, we don't know the properties of those compounds. So basically, the changes you make in the tuning process should be increasing in magnitude as you go to heavier and heavier components. And often the C36 plus, or the heaviest component, has its own set of correction terms, changing the default estimated properties, because those estimated properties are definitely not well known, and you can allow bigger changes because you simply don't know much about that. So you basically have increasing uncertainty going to the heavier and heavier components, and that should be reflected in how you change or tune the equation state.
On this slide, first, you have these, in the previous slide, you have these lines in the top, like you are correlating.
Oh, okay, here. Yeah, so this, so what's being shown here is basically how these properties relate to each other for these heavy ends, okay? So what you can measure, for example, using a distillation type experiment, you can measure molecular weight, specific gravity, and normal boiling point, maybe out to C20, 25, okay? So you can actually get those properties, correlate them. Those will definitely give some indication of how to estimate TC/PC, acentric factor, and this S term. So these lines here are basically saying that, well, molecular weight, if it's a paraffinic or an aromatic molecular weight, it'll be reflected in the boiling point TC. So these are all interrelated, and most of the PVT software have correlations between these so-called inspection properties, molecular weight, gravity, and boiling point, and the EOS properties themselves. So you might want to change, instead of changing TC/PC, you might want to change the boiling point, okay, to change that will affect the TC and PC and acentric factor, instead of changing directly these three properties here. So you have different ways of going about that. So if we look at the total number of potential variables in doing EOS tuning, this is the max. So let's look at, we've got EOS variables, that would be the 5 properties of each component. We're going to stay away from C6 minus components. So we've got 5 times the number of C7 plus fractions. And people like Keith Coates and others have shown that you need at least 2 or 3, at least 3 C7 plus fractions to describe miscibility, vaporization, etc. So at a minimum, we've got at least 3 of these fractions. A lot of the work we do and the laboratories give you probably at least 35 C7 plus fractions with all the isomers. You may have as many between 3 and 35 of these C7 plus compounds, times 5 properties with some uncertainty. The BIPs, the number of BIPs is in the full matrix is the total number of components squared minus the total number of components, that being divided by 2. That gets to be a very large number very quickly. Total number of components ranging from 13 to 45, typically. So if you start looking at adding these together, basically this needs to be added together to get total number of potential variables. In addition, we've got the sample composition uncertainty, and we have 3 different ways to adjust the composition in a consistent way. So we got 3 potential variables for every sample. So typically in studies we do, we'll have between 5 and 50 samples, okay, with full PVT data sets. At a minimum, you got 1 sample, a discovery well, for example. So the point is that if you put all these together, put them in the equation, you end up anywhere from 100 to 1,000 variables that can be changed, but of course, that's not where you're going to go. And I can just make a comment that most of the EOS modeling work that we've done over the last 35, 40 years have maximum 5 to 10 EOS variables, and 2 times the number of samples as composition variables. Now, how do we do that? That's a very good question for you to write in, and we'll talk about that the next hour. How do you do that? Okay. The point I'll make now is that these variables that we're talking about here will probably affect the TC-PCA century factor of all of the C7 plus components, but in a correlated way. That's just, but come back to that with a question if you're interested in. And typically these two that we're typically using here is the molecular weight, for example, C7 plus, or the molecular weight of the C10 plus, and the recombination GOR. These are the 2 composition variables. Now, the third variable, this gas chromatography, internal standard, baseline shift type problem, we try to weed out the uncertainty and potential errors of that data in a pre-processing step before we start the EOS tuning. So that's another good question, how that's done, but we can move on. So what is the mechanics of EOS tuning? So what I mean by the mechanics of EOS tuning, this automated minimization of the mismatch. So basically, we want to change these model parameters. We've got literally hundreds to 1,000 maybe that we can choose from, so that the model minimizes the mismatch of measured data. That is, it gives the best fit. And it's subject to the various constraints on how much we allow different variables to change. C10 component, the change is much smaller than the C30 component. In addition, you have to take into account the particular characteristics of individual and groups of data. So saturation pressure, for example, you may have an accuracy that varies from plus minus 5 psi for some samples, low GOR oil, to plus minus 500 psi for some dew points. Okay, you have to take that into account. This is the function that will, or this is a function that you basically are trying, it's called an objective function that you're trying to minimize. It's basically the sum over all the data, which will typically be in the hundreds, if not thousands. You've got a residual, which is basically expressing the difference between the data calculated by the equation of state here, minus the data measured by the laboratory, and then you divide by some reference data value that's appropriate for that particular data. Now, most programs will divide by the lab value here, but I'll mention why that's not a good choice. And so some programs don't do that specifically because it's a very bad choice for data like compositions, relative oil volume of condensates. It's a very bad choice to use. So this is a generic definition of the residual, and it's what's used in the software that we use here at Whitson called PhaseComp. We'll come back to that. Basically, you sum those residual and you weigh each data individually for various reasons. We'll come back to that. But let's say you've only got 2 saturation pressures, but you got 600 densities, relative volumes, gas-oil ratios, but you only got 2 saturation pressures. But you want those saturation pressures predicted accurately. The only way to get that is to weigh those 2 saturation pressures with a weight factor higher than the other data. So anyway, this is basically, we're going to minimize this function. And so now we're going to talk about the characteristics of the PVT data. First of all, we have what I consider a very heterogeneous type of data. We got very many different types of PVT data: saturation pressures, relative oil volumes, gas densities that may range from 2 kilograms per cubic meter to 900 kilograms per cubic meter. Well, the gas will probably only go up to 400 kilograms per cubic meter, but the oil might go from 400 to 1,000. So you've got orders of magnitude ranges in the densities, Z factor usually only of gas. Compositions, of course, for some components will vary from 60% methane to 80% methane. But for the C36 component, it might vary from OOX to 0.3. And so basically, you've got a lot of types of data. You've got a huge range of magnitude variations. Part of that comes because of units, which is easy to normalize out. And then you've got the weight factor, which is going to have to handle this issue I mentioned about like the saturation pressure, where you have very few of those relative to all the other types of data. And then you've got just the basic uncertainties in density, plus minus, let's say 2 to 3% experimental density error. Dew points might be 0.5%, it might be 5%. So you've got different uncertainties, and some properties will actually have an uncertainty, a lab uncertainty is what we're talking about here. Lab uncertainties that vary as a function of the magnitude of the property. Okay, and we'll look at that. So we need, and depending on these, the weight factor that you choose for different types of data and the reference data that you choose for different types of data will vary. In the case of magnitudes, you can just handle that by the reference data. Weight factors generally used to take into consideration how many of a particular type of data you've got, and then the lab uncertainty can affect both the reference data value used and weighting. This is just an example for 3 types of data where we've got the property, relative oil volume, composition of a component in the gas phase or the oil phase, and the magnitudes going from 0.001 out to 1. So many orders of magnitude variation. But because the laboratory uncertainty in oil volume is some physical fraction of a cc or something, the error will actually go towards infinity when you go to low enough relative oil volume. Likewise, for chromatographic analysis, there's a certain area of integration from the gas chromatograph that you can measure, and if it's lower than that, you basically don't know how much is there, and that will affect in the same way the uncertainty of those components with very small amounts. Needs to be dealt with. Probably only one PVT program deals with this and how they define the residuals and the weighting factors. Now, once you've developed the equation of state, how do you know that it's relatively unique or not unique? And the problem is that with so very many tuning variables that can be chosen, the wide range of data, the amounts of data that you might have, types of data, any given tuned equation of state developed by me or my colleagues or whoever it might be will lack uniqueness, okay? And so I'm going to talk about what will help us reduce the uniqueness problem. So first, you'll see the lack of uniqueness if all of those participating in this webinar were given the same set of PVT data, let's say just a simple depletion experiment, composition, and off you go with your PVT software, and everybody comes back with their equation of state. And let's say that, half of us get a good fit of the data and half of us don't. So we throw away the ones that don't have any good fit of the data itself. But let's say a couple of hundred of you come back with an equation of state that fit all 200 or fit all the depletion data. But then what we start doing, we calculate minimum miscibility pressure, vaporization by a dry gas, if it's a gas condensate, etc. So now we start calculating outside the range of pressure, volume, temperature, and composition of the data we use to develop the equation of state. And what you'll see is that you get this wide variation of extrapolated properties, okay? So in order to minimize the non-uniqueness problem, You basically want to have the more data you have, the more data, just literally the number of data, the more complex the data, and the more accurate the laboratory PVT data itself, the more unique your equation of state will be of your data, of your fluid system. You also have to be careful about which model parameters are selected to be changed. For example, if you allow big changes in C7 and small changes in C36 plus, maybe you'll get a good fit of the data you have, but you probably won't extrapolate very reliably. And then how you select the weight factors. There are many issues there that you can ask questions about. That there are many issues to take into account here. And what you're trying to do with adjusting the weight factors, you're trying to carefully, properly maximize the use of either the most relevant data or the most accurate data or both, and lesser emphasis on data that are uncertain or not important. In addition, the more samples that you include in the EOS tuning process, particularly in systems where you're going to see a wide range of composition change during the development of the field through depletion, gas coming out of solution, condensate coming out of solution, gas injection processes, will cover a wide range of composition. The more PVT data you have covering the entire composition space, the more unique your equation of state will become, and also the more difficult the EOS tuning process. The more time it's going to take, the more money it's going to cost to get all that PVT data. So once you've done that and you're satisfied with the equation of state, how do we check the thermodynamic consistency? That was kind of the constraint of any EOS model. And we have a few tests that we like to run on the final equation of state, be it ours or somebody else's. And basically that if you look at the K values, the equilibrium K values, at different pressures and temperatures, the ordering from high to low of K values should basically remain the same. The components with the highest K values should be the highest K values at any pressure and temperature and composition, okay, in general. So that's the first thing we go looking for. The monotonicity of component K values generally will decrease monotonically as a function of the normal boiling point temperature, TB, or as a function of the vapor pressure at a specific temperature, or you can actually even correlate it as a function of a calculated K value at some standard condition. So these are different ways to look at the data to see whether the K values are misbehaving, if you will, or changing their fundamental behavior. If that changes at different pressure, temperature, and composition conditions, that's not a good sign. Next is that if the laboratory has not observed and you don't expect any vapor, liquid type behavior, okay, physically you can actually have a mixture that splits into a heavy hydrocarbon liquid, a lighter hydrocarbon liquid, and a vapor. It can happen, like if you inject CO2 at low temperature, it happens all the time, West Texas CO2 floods. But in most reservoir systems, you don't see that in normal operating conditions. But if you start tweaking the equation of state parameters, either the BIPs and or the heaviest component properties too much, then this three-phase behavior is going to start showing up in the equation of state calculations. So you need some way, your PVT package needs to tell you that, well, it's calculating three-phase behavior all over the place, or in surface conditions, or somewhere. So you need to do this search, because if you take that equation of state to a reservoir simulator and it's computing physically, or not physically, but if it's thermodynamically computing three phases, your reservoir simulator will only calculate two phases. Your simulation is either going to run very, very unstable and slow, or it's just going to crash. So you'd like to know that the three-phase behavior exists, and if it does exist, and it shouldn't, you have to get rid of it. So it's going to be related to the tuning process. Another thing that we see almost all the time is that if you take the basically the density, liquid density of the components, and here we're talking about our C7 plus components, at standard conditions, divided by water density at standard conditions, that's nothing more than the specific gravity of that component. But if we take and calculate this from the equation of state with the TC/PC asymmetry factor, volume shift, and molecular weight, and look at that versus molecular weight, this should be starting around 90 for the C7 plus fractions, there should be some kind of trend that looks like this. And all of the PVT software start with a trend that looks like this. Increasing gravity with increasing molecular weight. But we see it in probably 10 to 20% of all the EOS studies we get from other people, is that you get, change color here, maybe this component is okay, this component is okay, and then you get something like this, something like this, something like this. For the, let's say, 5 C7 plus fractions. So why is that happening? Because it happens a lot. This happened all the time in PVT-SEN until about, I think, 4 or 5 years ago. Because you could change the TC/PC asymmetric factor and molecular weight independently, and it would keep the volume shift factor that it started with. Okay? Most simulators, most PVT simulators, will always bring, if you change the TC/PC or asymmetric factor or molecular weight during the tuning, it will always find a new volume shift factor that keeps you on the straight and narrow of that red line. That's the way it should be. And if your software does that, you'll always be getting good oil densities, be it at surface conditions or reservoir conditions. But if your software doesn't do that, you change the TC and the PC to get some, saturation pressures improved or some liquid dropout curve improved. And the volume shift factor, if it's kept the same in your simulator, this is what you get. And you won't see it because that simulator is not going to be calculating. You have to do this manually. You have to do the calculation of the individual C7 plus fractions as a feed equal to 1, C7 to C10, whatever it is. Take it to standard conditions, calculate its liquid density, specific gravity, and just see where it falls on this trend. So it's very common that you get, and the reason is because you're doing inconsistent and or independent tuning of the C7 plus properties. That's a very common mistake. I don't know how we're doing on time.
So about 1 hour now. So I think this is a perfect next topic.
So basically, we're going to round off by just talking about the history of EOS tuning. And the first 4 items I've got here is Ken Starling in SB, I think it was SB JPT or SBJ, 1966. I was using a BWR. It's not a cubic equation of state. Suave in 72 was doing EOS tuning to the original Redley-Kwong, and for every component, he was coming up with this correction term to the A, alpha. So he was doing EOS tuning there for pure compounds. Starling was doing it for all of both pure compounds and mixtures, using K-value data for the mixtures. Schoen-Prausnitz did work on mostly binaries to come up with the Kij values for important binaries. And Katzenfer-Zabadi looked at the Pang-Robinson equation of state in 1978, just after it was published, and showed that you need to match all of the K-value data coming out of the University of Michigan, required binary interaction parameters. So I'm just going to show you here. Try to. Okay, this is the paper by by Ken Starling, 1966. Basically, in principle, he's using a sum of squares function, which is the deviations of k values, experimental versus the EOS, or experimental, squaring it and minimizing this to come up with the parameters in the BWR equation of state. Chu and Prausnitz, who came up with the binary interaction parameter correction term. You can see some of that, probably hard to read it, but you got methane CO2, propane methane, butane methane, pentane methane, hydrogen sulfide, benzene propane. And you can see none of these binary interaction parameters are zero, as would be default, for example, in PVT-SIM for the SRK equation of state. They aren't zero. They might be close to zero, but sometimes 0.02 has a big impact on a particular binary to help improve the vapor-liquid equilibrium of that. So they did this tuning with the binary interaction parameters. Suave in 1971. It's possible thus to obtain from experimental vapor pressures a set of correction terms, tuned alpha values for the substance. It has been done for hydrocarbons, etc. And by the way, the Suave correlation works actually well for things that were not hydrocarbons, like water and non-hydrocarbons, surprisingly enough. 1978, petroleum mixtures. They basically show here, it's hard to see it, the binary interaction parameter between C1 and the different compounds based on binary data, as well as fits of data. See, here's fits of data for petroleum mixtures, and this is the binary interaction parameter between methane and the heaviest fraction for these different fluid systems where they had measured K-value data. 1978. And then 1982, Coates and Smart did the first EOS tuning of the type that we do today. Okay, they basically they used not sum of squares, but basically it was a linear regression, non-derivative based method. They looked at, I think it was 4, most of which were near critical gas condensates, 5 oils, some with gas injection tests. They came up with a recipe for fitting. This is just some of the fits from, they gave all the PVT data, they gave all the compositions, they gave all of the tuned EOS models. They looked at the Pang-Robinson and the another variation of Redlich-Kwong. And you can see this is for nitrogen injection into gas condensate. This is the near critical gas condensate volatile oil. This is a multi-contact vaporization test where you're getting, through this regression, you're getting an almost exact fit of the changing oil properties as it's being vaporized. And this is a near critical volatile oil. And for all the systems, they give the calculations, the comparisons, predicted and regressed. This was work by ARCO. This was the PVT package developed by Aaron Zick in 1986. It was used for the Prudhoe Bay design of miscible, the largest gas injection project at the time in the world. Basically, in that paper in 1986, talks about all of the EOS characterization work that was required to understand and study miscibility. Here's some of the PVT match data that they show. This is a swelling test going from the original oil, crossing through a critical transition and into a gas condensate with different amounts of gas solvent being injected. K-value being fit as a function of the different contacts. And then we're back to 1987. Actually, this paper was written in 1985, where Pedersen says that there's no a priori reason to believe that the EOS parameters tuned will lead to improved predictions of K values at other temperatures, pressures, and compositions. More likely than not, the predictions will be worse due to experimental errors in the compositional and other experimental data to which the parameters are tuned and model imperfections. Well, everybody was doing it by this time. Coates had done it, ARCO had done it, it was being done, and it has been done, and it continues to be done until today. So that's basically the conclusion. I wanted to mention that. Get this going.
You also have this 2000 PVT in between.
Yeah, let me just flip back to the original presentation. Oops, wrong direction. So this was just the summary of the Coates and Smart, the methodology that they used. Details, they didn't have volume shift when they started doing the work in 1980. Volume shift hadn't been introduced. It was a big, deficit. But basically, they had a proof of concept that it worked. Okay, that you could do EOS tuning for very complex and a wide range of fluid systems. This is the reference to 86 to ARCO, EOS phase. There was a couple of papers out of DTU where Mikkelsen, Pedersen came out of this group there, has done a lot of fantastic work through the years. A couple of papers that basically were very pro tuning equation of state. And then there was this paper by Pedersen and co-authors basically saying don't do it, or be very, very careful if you do it. The software that I developed and was first commercially available in '88, PVTX, now it's, I think, Roxar Emerson, who sells this, had complete EOS tuning capabilities. The first version of PVT Sim came out also in 1988, but without any tuning. And sometime between 1990 and 2000, they included the tuning, which is now in PVT Sim. I'm not quite sure when PVTI and WinProp came on the market. It was around 90, maybe a little before 90, a little after 90. Of course, Petroleum Experts, PVTP, came in later. And then the software that we use have since early 2000s. Phase Comp is a complete tuning package. It's really a phenomenal package. It's the ultimate EOS tuning tool, but it has the requirement. There's no graphical user interface and all of the bells and whistles that most PVT software has, but it does an incredible job in allowing you to deal with large data sets, many samples, very complex regression conditions, and is both fast and robust. So I think with that, we can stop. I apologize for going a little over time.
Yeah, perfect. Excellent, Curtis. Thanks. So we've got a lot of questions, and I've tried my best during the session to answer at least a few of the straightforward ones. And in this Q&A section, I've tried to include most of the questions, and hopefully Curtis can answer most of them. So we'll see. It's a good range of questions. Some of them are a little bit field specific, and other are more generic. But one thing I would like to say before we go into the Q&A, so we got a lot of questions whether the recording will be made available. And what we'll do, we'll send to all the participants that have participated in an email after the I guess later today or by the end of this week, we'll send the link so you can access this material if you want for later. Good. So I guess I'll just try to start from the top, Curtis, and move the way down in terms of questions. So there's a few questions related to.
Trying to figure out how this to maximize this somewhere.
Yeah.
It's maximized.
Good.
Let me just get out of this. Okay.
There's a few questions related to binary interaction coefficients, and I just want to group them maybe in the same question, but I'll mention both of the questions right here. Is it recommended to set binary interaction coefficients to 0? That's one question. And a second question, which is a little bit in the same alley, matching multiple experiments, especially swelling tests, usually require changing binary interaction coefficients. I always assume they should be as close to 0 as possible. Is that true? So on that note, I guess a little bit in terms of binary interaction coefficients, non-zero being 0. You mentioned some ranges for binary interaction coefficients. We also got a little bit related question as well to binary interaction coefficients, where we've come up with some negative values for binary interaction coefficients. What do you think about negative binary interaction coefficients?
Okay. Yeah, so just to reiterate what I'm going to go from red to blue, what I generally prefer. So just to repeat what we talked about, that for non-hydrocarbons, okay, which would be CO2, H2S, and nitrogen, and basically any hydrocarbon, C1 up to C36 plus. The published values will be ranging from about 0.05 to 0.15. Okay. And will be slightly different for Peng-Robinson and SRK. Okay, but so SRK values will be slightly different than Peng-Robinson, but they'll all be in this range. So that's probably the first, general comment. The second general comment is that between methane and the various C7 plus fractions, the normal, most programs on the SRK, the default here will be 0. In fact, it'll be all of the hydrocarbon will be 0 as a starting point. For the Peng-Robinson, that paper by Katzenfiersabadi that I referenced to, they made it very clear that the C1, C7 plus will typically default to something starting maybe for C7 around 0.01, 0.02, and going up to as much as 0.2 for maybe the C36 plus type number. So maybe for C7, something like that. So basically increasing positive, be increasing in positive for the heavier and heavier components. This was what Katzenfiersabadi found gave a best match, best fit to petroleum mixtures. And they were fitting equilibrium K values as a wide range of pressure, temperature, and overall composition. Okay? So those are general comments. I'm going to come back to this. Most software will have something like this as a default. So what I'll say is that although in general hydrocarbon BIPs are generally positive in the literature, there is no fundamental reason why a bit might be less than 0. Okay, so you see these negative bips in different EOS characterizations by a number of people. So there's nothing wrong with that. There's nothing fundamentally can be said wrong with that. And I'll just remind you that, remember, this A is the summation of AI, AJ, square root 1 minus KIJ. Okay. This is a correction term. There's nothing physical about it. I mean, now, Chu and Prowsen discuss how you can estimate the binary interaction parameter from physical properties. So there is some link there, but that link is not through equilibrium considerations. It's molecular size and so forth. It's a correction term, and really, in that sense, the total correction term is by default 1, and normally it's less than 1, you know, maybe ranging from 0.8, but there's no reason why it can't be 1.06, 1.03, which would be a negative bit. It's just a correction term. If it gives you a much better description of your fluid system, then there's no fundamental reason for not having a negative bit. Okay. Let's see. There's another there's no reason to avoid regressing on BIPs for the SRK or hydrocarbons. Just because Karen Pedersen has said that, or somebody says that you shouldn't do it, doesn't mean that it's right. In fact, if you look at the paper, I'll just go to it real quick, by Chu and Prausnitz, okay, there's nothing about what the binary interaction parameter should be for a particular equation of state. They talk about it generically, and this I'll just open this. You can see these values: butane, methane, pentane, methane, and so forth. They're non-zero. They are positive. They're non-zero, and these are expected to be required if it's SRK or the Pang-Robinson. So I don't know exactly how I want to, in a polite way, say that there's no reason that you shouldn't tune BIPs if you're using the SRK. Maybe the magnitude of them will be closer to 0, fine, but that they should be 0 because someone says they should be 0 is not right. I think that answered most of these questions on the defaults and.
Yeah, perfect. I think the next question we can talk a little bit about, there's several questions on the topic, a little bit related to kind of these consistency checks of the thermodynamic and physical consistency checks that we talked about in the end of the presentation, and mainly maybe related to monotonicity. So there's one question whether this these monotonicity checks is typically available as standards in different softwares. The second question is, how can we actually remove this potential monotonicity error while doing regression? And the third would be also require monotonic behavior for PC and TC.
Yeah. Monotonicity. So I don't think anybody has built-in testing for monotonicity. We do it manually after every EOS characterization, or if we get a EOS characterization, we basically do two plots. We do, for example, a CCE, constant composition expansion simulation, from saturation or from atmospheric pressure out to the saturation pressure at, let's say, reservoir temperature. And then we just simply plot pressure, probably on a log scale. If you use bar, here 1, 10, 100, 1,000. And of course, the K values will also be on, so this might be 1 and 0.1, 0.01, 10, and so forth. So basically, we'll make this plot, and let's say for C7, it's going to look something like this, like that, and then come up, and then maybe it'll, at the dew point or bubble point, it'll stop here. Methane will be coming down something like this. So that would be methane. And we look at every component, and we just make sure what we're looking for is that we make sure that, for example, C8, which I'll just use dashed line, that C8 doesn't look something like this, where it's crossing 1 or 2 times. This would be kind of a red flag. Basically, you got this crossing here and here maybe. That's a red flag to us. Now, the question is how to deal with that, or how to remove it. The crossing K values is almost always related to the BIPs. Okay. So if the BIPs don't change in kind of a continuous way, you know, it could be for, let's say, methane C7 to C36 plus. Not changing smoothly, or there being discontinuities in BIPs. Okay. Okay. That's typically going to be the cause of this type of problem. So you're going to have to revisit and either force kind of the BIPs to change in a smoother way or a more continuous way. There's a number of tricks but basically it's going to be linked, I think, 99 out of 100 times to BIPs. And it might be something like, let's say C1, and we're looking at C7, C8, C9, C10, C11, something like this. So maybe it's increasing like this. And then it goes to something like that. Even this amount of contrast might lead to crossing BIPs, crossing K values. This would be a discontinuity, a change, particularly if it goes to minus 0.02, but it doesn't have to be changing from positive to negative or have anything. So it's typically related to this. And the only way to get rid of it will be to probably redo the EOS tuning with tighter constraints on the binary interaction parameter.
Right. And a follow-up question on that was, is it required to have monotonic behavior for PC and TC?
Yeah, that's good. Yeah. So,
there's a lot of questions. So
huh?
there's a lot of questions. So
Okay. On that, there's a lot of that question or many questions. Okay. All right. So the thing is that the question is, should TC, PC, acentric factor, and maybe even volume shift. You could even include molecular weight, I guess. Molecular weight be monotonically changing? Question. Okay. Molecular weight, yes, if you're talking about in general, okay? I mean, you could have isomers. I mean, if you have isomers, the C7 single carbon number C7 includes benzene. And so you might see some non-monotonic there, but in generally, yes, for molecular weight. Okay. For everything else, basically you don't require monotonicity to have a consistent thermodynamic model. You can plot it. In other words, if you have TC being non-monotonic in one way, you can compensate that by the PC being non-monotonic in another way. So that what you could say is that maybe A and B, if you're going to look for monotonicity, you should look at it in terms of A and B, not the individual properties. But even here, A and B don't have to be monotonic. And the reason is because you have this binary interaction parameter, which can again compensate back maybe some slight non-monotonicity of even A and B. So what you really want, K value takes into account all of the properties and the binary interaction parameters. It composites all of these properties, okay? So that if this is monotonic, as it should be, it could be cancellation of non-monotonicities or changes in the individual properties. It's probably not what you want to do, but we would not classify a plot of non-monotonic TCP acentric factor as being a not valid equation of state. And in fact, I'm going to show you a figure. The default PVT sim characterization. On the paper. I think I've got it here. Yeah, maybe I don't have it here. It was in 80. I don't have it here. If you look at the acentric factor is always looking like this from the Pedersen correlation. You plot molecular weight, acentric factor, their correlation goes like this. If you just look at the numbers.
Good.
So you don't need monotonicity of really anything but the K value, and that's why we emphasize the K value, because it composites all of these, the variations of these components. So.
Great. So now we have a few questions related to, I guess, wax and asphaltenes. So I'll try to group them in one question. So do we recommend to use cubic equation of state models to predict phase behavior of asphaltenes and or waxes? And is there a way to predict occurrence or possibility of asphaltenes using equations of state, or is it typically beyond EOS applications? There's also a little bit related to that, probably a little bit more on the paraffinic side, but or paraphinicity side. So the libraries of new software store the property of the single carbon number components as an average value. How can we deal with this issue when we, for instance, have a paraffinic oil? So maybe not that relevant, a little bit relevant for the same question.
Okay, yeah. So the first one, generally, these are not something that we do a lot of work in, wax and asphaltenes, but the cubic equation of state purely by itself is basically not used. Now, for wax, it could be used, okay, but probably not without some adjustment. Certainly not for asphaltene, but not generally done. I'm not going to say that it can't be done, because you can, with the cubic equation of state, you can give it properties, BIPs, and the heaviest component having very heavy properties. You can get the cubic equation of state to give you a valid vapor in equilibrium with a valid liquid in equilibrium with a solid or a very, very heavy liquid containing mainly one component, or the very heavy components. So you can actually do that, but you would have to tune the properties of that very heavy component, maybe some BIPs, in order to match observed wax or asphaltene type data. And asphaltenes, you probably could just have a single component being introduced, very, very heavy component. Whereas for wax, you probably need the single carbon numbers. For example, for wax, you would need, for C greater than C20, you would probably need a paraffin aromatic split of each single carbon number. In fact, I think this is what PVT-SEM kind of does. It takes the distribution C20 heavier, and it splits it into a paraffin aromatic type. I don't know exact details of it, but basically because wax starts precipitating for these heavier components around C20. So you would need something like that, which is probably not in many software. And for asphaltenes, you would basically need some C, I'm going to call it M+. This is M for monster. Properties. Some component that's going to start precipitating out as a function of pressure, as a function of composition. If you add gas to it, you would have to tune it. You might need more than one of these components. It's not done in a standard way, but I think the cubic equation of state can precipitate heavy phases that would look like wax and might look like asphaltenes, but it's just not generally done. Now, when it comes to the fact that almost all PVT software operate with an average single carbon number set of properties, whereas we know each single carbon number contains many isomers, maybe mostly paraffin, but we just did a study on a gas condensate system where in the C7, 8, and 9, there was slightly more aromatics than paraffins. It's unusual. So the question is, I'm not sure what the question was, but sometimes so you might need a C7 paraffin, a C7 aromat. You maybe just need the CN plus to be one paraffin. It's not paraffin, it's paraffin-like properties, aromatic-like properties. So all I'll say is that there are some situations this is either highly recommended and or required. Okay, and those would be, like you say, for example, a gas cap that's maybe more paraffinic than the oil, equilibrium oil zone, which might be more aromatic. Very good example of this is the Mullen-Pyatt field.
And funny enough, there's actually a question 3. What is the process of creating an EOS that can describe the mixture of two different oils? For example, a high GOR fluid with wax and a low GOR fluid with deposits.
Yeah, you have to do something like this. And in fact, we did the fluid characterization for Oxy before they got out of the Mullen-Pyatt field, because the gas cap had a very clearly more paraffinic C7 plus than the oil. So this is how you have to do it. The Shell C7 plus characterization method from the 70s, Tom Schulte in that group, and until they threw away all of their internal software and got a corporate license of PVT-SIM, their default characterization method had 14 C7 plus components, basically 7 fractions. Each fraction had a paraffin and an aromatic. So all of the Shell characterizations were done. So this is the one situation. The second is compositional grading in general. This is very clear from the paper by Tom Schulte in his classic 1980 paper on compositional grading calculations. This is in the Middle East, where they had very clear API variations that you'll never, ever predict in the oil column without having a paraffin aromatic split. These are 2 examples where you might need to do the separation. I think also on viscosities, we've seen in the Middle East, some of the fields, sometimes you need this here simply to capture the big oil viscosity variations you see, let's say near the water contact. So there are situations, but you're going to have to do it manually. I don't think any of the softwares offer some kind of automated way of doing it. You'd have to do it manually. But it can be done, and sometimes it should be.
Excellent. So now a little bit on that, maybe a little bit related. It's more, or another topic, I guess, which is more about representative fluid samples and using representative fluid samples when we create or tune equations of state. Some of the questions, there's a lot of questions on this topic, so I'll try to condense it a little bit, but essentially, can we use contaminated samples in EOS model tuning? That's one. How can we actually declare whether a sample is representative or not? Let's say we have 3 different samples of so a separator oil and separator gas for a condensate well. How do we actually pick the best sample for recombination?
Okay, so what I'm just going to say is for EOS tuning, sample selection. use all samples that are not oil-based mud contaminated. Okay? That's just a general rule. If you only have, in like a discovery well or a delineation well, if you only have open hole formation test samples with contamination, then of course you have to use those. Okay? Basically only use oil-based mud contaminated samples. If that is the only type of sample you have. So I think the Magnolia field, I think that was in the Gulf of Mexico. We had a study with, like, apparently the permeabilities were so high or something that they only had the oil-based contaminated samples the first 3 or 4 wells. They had a whole bunch of samples, but they were all contaminated. We had to develop the equation of state with those samples and their PVT data. And then after doing the characterization, we then basically we threw out the contamination component amounts, and we're left with what we had our best estimate of the equation of state to use.
Is there any contamination level we should consider, like 10%, 20%?
Well, if you only have contaminated samples, I would again use them all. In fact, because sometimes we've even recommended that when that was the case, for the laboratory to make up new samples, let's say with 8% contamination, to make up 2 new samples, adding contaminant to 15 and 25%. And then we tune the equation of state for 8, 15, and 25% mixtures. And then you, in a sense, you have a better feeling of the accuracy of the decontaminated composition. So yeah, I would use them all if this is the situation, irregardless of. Yeah. Mm-hmm.
Excellent. So there's also a question on representative samples. It's a little bit more field specific about a mature carbonate reservoir field that was an initially undersaturated black oil with moderate strong water drive. And after 20 years of production with many wells, the first 3 to 6 months of early production data were used to when the GR was fairly stable, still above the bubble point. And this producing GOR was then compared to the GOR in the laboratory PVT report. It was actually observed that the actual production was 40% lower than the lab observation. So follow-up questions here is, which initial GOR should I believe more? And what about experimental errors? So then I guess for history matching purposes.
Well, okay. The thing is, this is a question related to maybe more towards fluid initialization, but since this topic of the webinar is EOS tuning, I think I'd like to say that we can't do anything in the EOS tuning from, I mean, basically early samples, PVT data, and current samples, PVT data. They should all be described accurately. By your equation of state. Okay? So if you did develop, you probably didn't, but if 20 years ago, but if they developed an equation of state for the early sample PVT data with whatever GOR it is, I don't care, lower, higher, whatever from now, I would take that equation of state, simply take the current samples and put in their compositions, maybe allow some variation only in the composition, see how well the EOS would predict that the new PVT sample, PVT data, okay? If you can't get to the new PVT data matched with the old equation of state, then you go in and develop a new equation of state, but you include all the data, not just today's data. And then once you get that equation of state that describes both original, early, and current PVT data, then you can start looking at, well, was the initial GOR this or that, or what's, maybe there's variations. You can start looking at the initialization problem. But for EOS tuning, use all of the samples that you have with PVT data. That's the general philosophy.
Right. So we have 9 more minutes. So I think a few of the next questions should be fairly quick to answer. There's one question for reservoir simulation of gas condensate reservoirs. What should be the minimum number of lumped components used, or in theory?
So the Coates paper, 1980, I think it was published in 85, it was presented in 83, I think, simulating gas condensate reservoirs. That's the name of it. That's the go-to paper specifically about that question. And what he basically says is that if you have depletion only, or gas cycling with reservoir pressure above the dew point, in either of these cases, you can use one C7 plus fraction or a Blackwell model. That's what he concluded. If you do gas cycling below the dew point, then he showed that you need basically 3, depending how accurate you want to make it, 3 to 5 is sufficient. Minimum 3, 5 maximum C7 plus fractions to describe the vaporization of that condensate. PVT. That's the go-to paper. Now, Singh authored a, I'm sure saying we have in our list of publications an extension of this to outside of gas condensates, the oils, but it also has one example of a gas condensate where these set of rules don't apply. I think it had to do with gravity, segregation, high permeability. So there is an exception to this. But so I'll just mention, do you remember seeing that paper number?
63087, I think.
63087.
Right. A few more questions here. So why don't you use omegas when you tune an equation of state?
Talking about omega in the equation of state?
Yeah.
Okay. Use omega A and omega B in EOS tuning. Well, Coates did, so you can do it. I've done it before. It can be used, and successfully as well. The question is, why don't people do it anymore? Okay, I think that's the question, is why don't we use the omega A, omega B in tuning? So I'd say that there's a couple of reasons. One, to understand physically the changes, you don't have a physical relationship with the omega A and B. I mean, we don't understand, in a sense, physically the physical properties change for a combination. If you change A and B, maybe the A makes it look more aromatic and the B makes it look more paraffinic, and so you have to do of the A and B corrections. I think that's one of the reasons people didn't like the Coates and Smart approach. That is that you couldn't get that. The second reason would be that you've got, TC, PC, and acentric factor are the physical properties. And you'd like to have some kind of a consistent change. Using these as regression parameters, this allows consistency in the change. For example, to avoid this crossing of K values or making C7 heavier than C8. You can change, for example, the normal boiling point in a way, and that will change all three in a consistent way. You don't really have that with the A and the B, unless you really study how A and B should be changing, and etc. So I think that's the second reason. And then the third reason is that the temperature dependence, if you're fitting reservoir temperature data, when you change TCPC acentric factor, this acentric factor that's basically correlating this temperature dependence of the vapor pressure for those components. And so if you just multiply by the A, that temperature dependence is being changed. It's not consistent with the temperature. So there's an inconsistency with you could potentially get an inconsistency of the temperature dependence could be worse because of doing it directly on A and B. So I'll just say temperature extrapolation may be less reliable. That's why I would not use it. Yeah. Myself, I mean, if you said I have a PVT package you only can change A and B, and that's the only software I could use, well, I would use it. So.
A very interesting question from Argentina. So specifically Vaca Muerta, the shale basin there. They're finding a lot of critical fluids, and they're discovering volatile oils with found at high initial pressure. So mentioned a pressure of 600 bar and low saturation pressures around 200 bar. We're experiencing big difficulties matching the undersaturated part of the CCE experiment with the cubic equation of state, which affects the compressibilities. What is your suggestion for this type of problems?
Mm-hmm. Yeah, I already mentioned that in saying that the cubic equation of state doesn't give the right oil compressibility. And so welcome to the club. Okay.
Yeah.
So so basically oil compressibility, pressure dependence, not right. It could also be gas, by the way, if it's high enough pressure at higher undersaturated pressures. Okay. So here's my fix that I've used in several fields because you want the recovery right. It's a big deal. So what you want to look at is that recovery factor of your oil, it's actually a function of the oil compressibility, the water compressibility, and the rock compressibility, right? And to make it more correct, it's oil compressibility is a function of pressure. Water compressibility, in most simulators, I don't think you can have it as a function of pressure. Is that right, Singh?
We can have
Water?
Yeah.
Okay. So you can have water compressibility as a function of pressure, and you definitely can have formation compressibility as a function of pressure. Okay? So what we're saying is that the cubic equation of state is wrong on this pressure dependence. Okay? So what you have to do is you have to have some kind of a pseudo water rock. You can do one or the other, because you've got changing water saturation around, changing oil saturation. So it's not a trivial matter. But basically, you develop some kind of pseudo water rock pressure dependence that compensates for this error. So basically, you want the total compressibility pressure dependence to be right. If you want to know how to do that or how you might consider doing that, you can contact us, maybe through a mail or something. And I have to go back and revisit exactly because it's, there's a number of combinations you can do. But that's the only solution. You cannot tune the equation of state and get the oil compressibility right. At least I've never figured out how to do it. I don't think it can be, but because the composition is constant. So.
Perfect. Now, probably maybe the last question, we'll see, but this is more related to, okay, you want to do equation of state tuning and you have no data available, or maybe you have one experiment, for instance, just a composition and a CC experiment. How would you then do equation of state tuning, or should you do it at all?
Yeah, so this paper, SPE 155499, and I have no life, I agree. That is a paper that where we wrote up a kind of a recipe for doing exactly that for unconventionals, where you had very, very minimal data. So there's a recipe in that. I think that's the starting point. And yeah, you can do it, but you're basically going to take your producing gas oil ratio. You want to honor that, your API gravity, and if you've got gas gravity, which you probably have, separator or average surface gas gravity, you'll use these properties just like we use in the bubble point, a standing correlation. But you basically use these to estimate a well stream molar composition, okay? And with that well stream molar composition, that goes into the equation of state. Well, the C7 plus properties that you assign, which is the unknown, molecular weight, specific gravity of C7 plus, basically these two properties you need, they will be selected such that you honor this API gravity here. And obviously it'll be approximate, but what we see in the unconventionals is that you often had a separator gas composition together with the gas gravity. If you've got this, you're good to go. Then you have really no problem creating a reasonable estimate of the well stream gravity, well stream composition, tuning the equation of state, C7 plus properties. You can get a reasonable well stream that you can do preliminary calculations with, saturation pressure, formation volume, black oil tables, etc. So you can do it, and I think this is a good starting point to how to do that.
Perfect. So I think on that note, we'll leave it at that. If there's any other questions, unfortunately we haven't been able to answer all the questions because we literally got hundreds of questions. So if there's any of you that has interest in particular subtopics of this, just please send us an email, and we see if we can answer them. And you can get all the contact information on our web page, whitson.com. And we are in general fairly quick in terms of responding. So thanks everybody for the webinar, and take care.